Hello and welcome to the video presentation here. As the next part of the unit number 4, we start with these rectifiers. Basically, the rectifiers are those circuits which convert the alternating electrical quantity into the unidirectional electrical quantities, means voltage and currents. And these circuits will be making use of one or more unidirectional electrical conducting circuit elements like diode. To go into the types of these rectifiers, we are having basically two types of rectifiers. One is the half wave rectifier and another one is the full wave rectifier. And in this full wave rectifier, again we are having two types. One is the center tap rectifier and the other is the bridge rectifier. We will see the working of all these rectifiers one after the other in this video. To start with these rectifier circuits, we should know the behavior of the diodes when they are connected in the forward biased and reverse biased configuration in the circuit. The diode, when connected in the forward bias configuration, it acts like a closed switch, conducting the current through the anode and cathode. When the same diode is connected in the reverse biased configuration, the diode acts like an open circuit and it will not be conducting any current through the anode and cathode. Due to this unidirectional conducting property of the diode, this is one of the reasons that this diode is categorized as an active element in the electrical circuit. You should note this property of the diode. Now, coming into the half wave rectifier. In the circuit, we are having a simple transformer. You can recall the block diagram of a power supply, the DC power supply, wherein the conventional AC input is given to the first block, that is a transformer block. Next, it is supplied to the rectifier block. And these two blocks are discussed in this session. Now, the transformer will be taking the conventional AC input and supplying to the rectifier element diode, which is connected in series with this load resistance RL as shown here. Now, we will see the variations of the input and output voltages through these axes here in the graph. During the positive half cycle of the input, the terminal P of the secondary transformer will be positive with respect to the terminal Q, and the Q will be negative here. The variations of the input and the output waveforms from pi to 0 to pi radians are as shown in the graph here, wherein due to this configuration of the input polarities, the diode D will be forward biased during this positive half cycle of the input, and the load current IL will be flowing through the circuit as indicated by the directional arrow there. And this load current IL, which is flowing through the load resistance RL from top end towards the bottom end in the circuit, will produce the voltage V0, which is equal to IL into RL in the mentioned polarity. Upper end of this resistance will be having the positive polarity and the lower end of this resistance will be having the negative polarity, because the current will be flowing from top end towards the bottom end of this resistance. The current always flows from the positive potential towards the negative potential, higher potential towards the lower potential. That is why the higher potential point is always mentioned as the plus here and the lower potential is always mentioned as the minus here. And this voltage V0, which is produced from 0 to pi radians, is almost similar to the input supply variations and is produced as seen in the output voltage waveform. Now, After this first half cycle of the input, from pi to 2 pi, when the negative half cycle is input through this input polarity, the terminal P and Q polarities will be interchanged. That is, P will be assigning the negative polarity and the Q will be assigned with the positive polarity. This polarity makes the diode D to be reverse biased and acting like an open circuit, and it will not conduct during this negative half cycle of the input from pi to 2 pi radians. Due to the absence of load current through this RL, V0 will be equal to 0 from pi to 2 pi radians as seen in the output waveform plot. In the next cycles of input, the similar behaviors are seen here by the circuit, wherein only the positive half cycle is transferred at the output and the negative half cycle is not at all transferred through the output. As only the half of the input cycles are produced at the output cycle and the output is a unipolarity variation, means the direction of current through this load resistance is in the single direction. It is unchanged here. That is why this rectifier is called as a half wave rectifier. Now coming to the next variety of the rectifier, the full wave center tap rectifier. This circuit uses a bulky center tap transformer. The beauty of this center tap transformer is that it is having two input terminals at the primary side and it is having three terminals at the secondary side. The upper half of the secondary and the lower half of the secondary is divided by the center tap terminal O, wherein the upper half voltage and the lower half voltages are exactly same but reverse in their polarity. Means if the upper half of the secondary of this center tap transformer is having a positive variations, the lower half of this secondary of the transformer will be having the negative variations at the same time. Now, this circuit uses two diodes D1 and D2 as shown in the figure here, and a load resistance is connected through these points to the center tap O there. The input voltages at the two half of the secondary terminals are mentioned like V in, which are exactly the same but opposite in their polarities. The input and the output waveforms can be plotted along these axes here. Now, during the first half of the input cycle from 0 to pi radians, terminal P will be positive with respect to the center tap O, and this makes the diode D1 forward biased and conduct the load current IL as mentioned by the red loop line in the circuit, and it will be flowing only in the upper half loop of the secondary circuit. As the Q of the secondary of the transformer is negative with respect to the center tap O, diode D2, which is connected in this lower half of the secondary, will be reverse biased and it will not conduct any current. Due to the flow of load current IL through the upper half loop of the secondary circuit, from right to left in the load resistance RL, it produces a voltage V0 which is equal to IL into RL in the mentioned polarity there. The right side will be positive and the left side will be negative here, which is plotted in the output voltage graph here, which always resembles that of the input cycle variations. Now during the negative half cycle of the input here, the polarities of the terminals P and Q and O are interchanged. Now the terminal P will be assigned negative with respect to the center tap O. This makes the diode D1 reverse biased, and the polarity of Q is now positive with respect to the center tap O, and this makes the diode D2 getting forward biased and conduct the load current as mentioned by the yellow loop line through this lower secondary loop there, wherein compared to the previous first half cycle input behavior, you can see that the direction of the current was from right side to the left side through the load resistance RL. Now in this second half of the cycle also, the direction of load current is from the right side towards the left side and to the center tap of the transformer, as the direction of load current is unchanged. Through this load resistance RL, the polarity across this RL, which is the polarity of the output, is unchanged. As in the previous case, it is again mentioned as positive in the output waveform, as you can see from pi to 2 pi radians in the output waveform. Now, the similar behavior of the circuit will be continued during the next input cycles of the input here. As the both positive as well the negative half cycles of the input cycles are converted to the unidirectional output voltages across the load resistance RL, this is definitely a rectifier which is converting both the half cycles, is called as a full wave rectifier. As the circuit is using the bulky center tap transformer, this full wave rectifier is called as a full wave center tap rectifier. Now the next variety of rectifier is the full wave bridge rectifier. The name is so called because of the type of the connection used in the rectifier configuration elements. This uses a simple transformer and 4 diodes. Compared to the previous circuit, 2 extra diodes are used. Diodes D1, D2, D3 and D4 are used. You can please mention and note down here clearly the polarities and the names of all these circuit elements connected. As you can see that the load resistance RL is connected in between the opposite edges of this diode structure here. It is acting as a bridging element between these 2 points of the diode circuit. That is why this circuit is named as a bridge circuit. Now, the input and output variations of this circuit are plot in these 2 axes here. During the first half cycle of the input from 0 to pi radians, the terminal P will be positive and Q will be negative. Due to this polarity of the input cycle, diode D1 and D3 will be forward biased and D2 and D4 will be reverse biased during this half cycle period from 0 to pi radians. The simplified circuit will be seen like this. Now, the load current will be flowing from the positive terminal of the supply P through this diode D1, RL, D3 and back to this Q as shown here. This load current IL, which is flowing through the load resistance RL from right side towards the left side, produces a voltage V0 which is equal to IL into RL with the mentioned polarity there across the load resistance, produces the voltage waveform which is similar to that of the input voltages here from 0 to pi radians. Now, during the next half cycle of the input, from pi to 2 pi radians, you can observe that the polarities of the input terminals at the secondary of the transformer P and Q are reversed. Now P is assigned a negative polarity and Q is assigned a positive polarity. Due to this reversed polarity in the transformer secondary terminals, diode D1 and D3 are now reverse biased, and D2, D4 are forward biased, and the simplified circuit is seen like this now. Now the load current will be flowing from the positive terminal of the supply end Q through this diode D2, RL, D4 and back to this P as shown in the arrow direction in the yellow color. As in the previous case, the direction of the load current is unchanged through this load resistance RL from right towards the left and produces the voltage V0, which is equal to IL into RL in the same polarity as was produced in the previous half cycle of the input. That is why the output voltage waveform in the output waveform from pi to 2 pi is produced or drawn in the same positive polarity here. Though the input is in the negative polarity, the output produced is the same polarity. Due to this unidirectional polarity output, which is derived from the bidirectional polarity input, this circuit is called as the rectifier circuit. As both the half cycles are produced at the output, it is called as a full wave rectifier. Due to the configuration of connection of these 4 diodes with the load resistance, it is called as a full wave bridge rectifier. Now in the subsequent input cycles of the AC, the outputs are similarly carried out and the outputs can be observed like this as seen in the graph here. The behavior and comparisons of all these rectifiers are entered in this table, wherein you can take a snapshot, pause the video, note down all these things, and a few of these will be derived in the coming classes, upcoming classes there. Okay, and with this I am signing off from here. In the next video we will see the next part of our discussion.